Hello and welcome to this video on solving quadratic equations using what's called the square root property. So in this video I'm going to introduce you to this square root property and also the steps that we're going to follow to solve a quadratic equation, right? An equation with a square as the highest power, right? A second power as the highest power on a variable. And I'm going to go through the steps to explain the steps for using this square root property to solve such equations, and also what to look out for, to determine whether or not you can use the square root property. And then after that discussion, I have several examples where I employ all the stuff I discussed. All right. So my first page, I'm going to discuss, what is this square root property that we're talking about in the title of the video for the solving of quadratic equations. All right. So what is this square root property? All right. So if we try solving a quadratic equation and we end up with an equation that looks like this, say x to the second power, right? The highest power on my variable is the second, making it a quadratic. If I end up getting it down to looking like x squared, or the variable squared equals some number on the other side, right? Where this n over here is just a number. Okay. So again, n is a real number. Right. Well, if you think about this, what numbers when squared give me n? Well, there were two possibilities, right? One was the the principal square root of n. All right, let's recap here. Recall over to the side. If you take the square root of n and square it, that is indeed going to be just n. But also, not just the principal square root, but also the negative square root of n when squared, right, will become positive, just n again. So there are actually two possibilities here. So this is what the square root property states. It states that if you have an equation that looks like this, a quadratic equation, some variable expression squared equal to some real number, then the possibilities here, what make this a true statement, is if x, right, the value of this base here, the thing being raised to the second power, it could be the principal square root of n, or x could be, again, the base x that's being raised to the second power could be the negative square root of n. All right. So yeah, so this is it right here. This is the square root property. Now, very often, instead of writing, I'll be writing out these two separate equations. Very often, you'll see people write, because they look so similar. One's just with a plus in front, a positive in front of the square root of n. One's with a negative. Very often, you'll see people writing out x equals positive or negative square root of n, like this. To represent both of these, one with the plus, one with the minus. And I will actually be writing out each one separately, as I find that people, even though they kind of think they know what they're doing, when people write out this plus or minus, I feel like they miss something. I feel like they think there's only the one solution when in fact there are two. All right, and then some things to say about this. I mentioned that we're trying to get our quadratic equations to look like this, where I have a variable expression squared equals some real number, right? I mentioned this n was a real number. So some notes on this. One, if n is positive, right? If n is a positive number, then the square root of n and negative square root of n are real numbers, right? Then the square root of n and this negative square root of n are real numbers. I'll just say they're real. So we'd have two real solutions to this equation if n is a positive number, right? We'd be taking the square root and even root of a positive number, which is real. But on the other hand, if n is negative, right? If n is less than 0, right? I have x squared equal to a negative number. Well, then that square root of n and negative square root of n, remember we'd be taking the square roots of negatives, and I've mentioned in previous videos, if you've been watching, when you see the square root of a negative number, right, you should be rewriting that with that imaginary unit I. That the square root of a negative number I'm seeing in both of these is a pure imaginary, right? Are pure imaginary numbers, or sometimes just referred to as imaginary numbers. All right, so then this equation would have two solutions with an imaginary part to it, with that number I, that square root of -1 involved. And then the third part, I've talked about when, if this is a positive number, you get two real solutions. If it's a negative number, you have two solutions with an imaginary part. But if it's 0, then there's only one solution, right? The square root of n and the negative square root of n, both of those would be the same. They'd actually both be 0, right? The square root of 0 is 0, and then the opposite of 0 is 0, right? So you'd only get one solution out of this, right? Where the value of n is 0. Okay, so again, I know it's a lot of letters here. I just have one more thing to point out. Right, when can we use the square root property? When am I going to be able to use it? So that's a question I'll ask here. When can we use this square root property? And the answer to that, if you're looking at your equation, your quadratic equation, where the highest power is a square, notice how there's a square, right, a power of 2. The variable in question, the unknown, is just part of the base of that square, part of the base of that exponent of 2, and then outside that square there is no variable, right? Yeah, there's a letter n over here, but remember this represents a number. That's not a variable. It's not unknown. So the answer to that question, if the square has a variable expression, right, so an expression with a variable in it as a base, and there are no variables anywhere else. There are no variables, outside the square. All right, so some examples. All right, here's an equation that I could use the square root property for. Say x squared plus 1 equals 3. We can use. And I'm just going to call the square root property here the SRP for short. So we can use the SRP here because, again, like I mentioned, see there's a variable inside the square, and apart from this square, right, there's the square. Apart from this square, there's no variables outside it. So we could use the SRP, and then I'll talk about how, all right, in a minute. If I have, say, x minus 2 in parentheses squared and then minus 7 equals 10, we are going to again be able to, we can use the square root property, the SRP here, because again, here's the square, right? The expression with the square. There's a variable inside of it, right? There's a variable in the base, and then outside that squared expression, there's no other variables. Right. And then here's one where we couldn't. If I had, like, say, x squared minus 2x plus 1, when's that equal to 13 or something? Here we wouldn't be able to use the square root property as is. All right, I'll say as is because we're going to see in a future video that if you see a quadratic equation where you can't use the square root property, there's going to be something you can do called completing the square to set up the equation so that you can use it. Now the reason for that is, look, here's the square, right? There's a variable inside that square, right? The x, but look at this. There's also a variable outside the square. Right, and that's why we can't use the square root property or the SRP as it looks right now. All right, so that's what I'm looking for in this video, in these examples. Is there, first of all, there's a square, and is there a variable inside that square? Is there a variable in the base? And is there any variable outside that square? Right? If there is a variable outside the square, I can't use the SRP right away. All right, there's something I can do later in a later video, but for right now we'll just say we can't use it. All right, and then finally, before I get into my examples, the steps involved in using the square root property. All right, so the first step is going to be to isolate the square. All right, that means get it into that form that we started off looking at. All right, where you have the square alone on one side and some number on the other, right? Remember, there shouldn't be any variables outside the square if I'm going to be using this SRP, right, the square root property. So get the square alone, nothing times it, nothing divided by it, nothing added or subtracted to it, just get the square alone. Then we're going to use the square root property. Again, I'm going to abbreviate that SRP. So that leads me to solving two equations. Remember, if x squared is equal to some number n, that means that x is either the positive or the principal square root of n, or could be the negative square root of n. And remember what I said earlier, if n is a positive number, these are two real numbers. If n is a negative number, these are two pure imaginary numbers. And if n is 0, you don't need to write both, because if n is 0, both of these are 0 and you just have x equals 0. Alright, then after I split apart, my quadratic equation into two linear equations, right? First power equations, first degree. We're going to then solve the resulting equations, solve each of these, because you might have to still solve for a variable. It doesn't look like that here, but solve the resulting equations, and of course, as with any equation solving, check your solutions back in the original equation always, right? But that's huge, right? Always check your answers. Double check to make sure you're doing things right. And check it back in the way it originally looked, right? Okay. So let's keep those in mind. And I'll leave the steps up actually, and we'll put off to the side. All right, let's leave them in the corner here. Let's clear some of this stuff out of the way. So leaving the steps up, here's my first example. All right, and what I'm asked to do in this example and all the examples for the rest of the video is solve the quadratic equation using the square root property. All right, so the first step, I have p squared equals 48. Notice that this is an equation where I could end up using the square root property because I have a variable inside a square and no variables outside that square, right? You're not seeing the variable of p anywhere else but inside that square. Alright, so first step, isolate the square. Done. Alright, the p squared is alone on its own side of the equal sign, and there's nothing multiplied by it, nothing divided by it, nothing added or subtracted from it. So great, that's step one. Then here's where, by the square root property, the values of p that would make this a true statement, p could be the positive or the principal square root of 48, or p could be, the negative square root of 48. And of course, then we solve each of these, right? Step 3, solve the resulting equations. Now, they are already solved for, right? P is already alone in both of these. So here are my possible solutions. Now, of course, I would like to also simplify any radicals as we go through. Please simplify your radicals. And I've put up videos in the past on simplifying radicals if you want to look those up, or just look up simplifying radicals and find other videos. I'm sure you can find plenty. So I noticed in both of these I have the square root of 48. So off to the side here, square root of 48, what is that? Now that's a real number, right? 48 is a positive radicand. This is the square root of a positive. This is real. So both of these are real numbers, not imaginary. And remember what we're doing when we take a square root. You look for a perfect square that is a factor of the radicand, a perfect. And that would be, 4, 1, cool, but the largest one that goes into 48 evenly would be 16. So that's the square root of 16 times 3, right? 16 times 3 is 48. A perfect square, 4 squared, times a non-perfect square. And since these are both positive and the square roots of positives are real, I can use that product property for radicals, break this up. Remember, that's only if the two numbers are positive. Only if these two are real can you use that product property to split them up. that product property was, remember, a property of real numbers only. And then what's the principal square root of 16? That's 4 times the square root of 3. All right. Okay, so my solutions, my possible solutions. The value of p could be, positive square root of 48, or this positive 4 times the square root of 3, or the value of p could be, the opposite of that, negative 4 times the square root of 3. And of course, as I've said earlier, right, when you're solving an equation and you find some possible solutions, check these things. Now I'm just going to go to a calculator here. I mean, you could pop them back into the equation as well. Here's a calculator. I'll put them right next to this. And I'm just going to put 4 times the square root of 3 in for p on the left side, see what I get. And hopefully it's 48, right? That way you'll have 48 equals 48. So 4 times the square root of 3 in parentheses. Right, that's replacing the p, and then squared, and look at that, it is indeed 48. I know that's kind of tiny there, but it is 48. And the same thing would go for this negative, right? If you plug in, if you take a negative number and square it, a negative real number and square it, it's going to be positive. So 4 root 3 and negative 4 times the square root of 3, both of those when squared will give me 48. So wonderful. I'll put a big bubble over both of them. All right, they're both good solutions of this equation. Wonderful. Okay. The next example. All right, same thing. I'm asked to do the same instruction. Solve the quadratic equation using the square root property. And again, I'll keep the steps up. So my next equation is this one here. I have 3 times b squared equals 75. So again, notice, right, that this is an equation where I can eventually use the square root property. I have a variable, b inside a square, right? It's in the base of the square. And then outside that square, there's no other b's, right? There's no other variables. So this is another quadratic equation in which I will eventually use the square root property. Alright, so the first step isn't done. Alright, the first step, I want to isolate the square. This is the square, right? The only thing being raised to the second power is the b, not the 3. Alright, the 3, if this was in parentheses, that'd be different. But the 3 is not in parentheses with the b, so 3 is to the first power. 3 is on its own, and only the b is squared. All right, so here again, here's the square. I want to isolate that. I want to get that by itself. Now it's multiplied by 3. All right, so I would simply divide both sides by 3. And that leaves me with b squared on the left side equals, and then 75 divided by 3 is positive 25 on the right. And now I have it in the form that I wish, right? The square on its own side equals some real number on the other side. And then we apply that square root property. Just going to put SRP, right? Square root property. By the square root property, right? This will be a true statement if b is this, the positive square root of 25, or the principal square root of 25. Or this will also be true if b is, the negative square root of 25. All right, and then of course I want to simplify my radicals. The square root of 25 is, 5. Remember, whenever you see this radical symbol, you're asked for the non-negative root. So this equation here, we have b equals 5, and then this equation here, we have b equals, the opposite of 5, or negative 5. Right? And don't forget to check. Right. Oh yeah, and solve the equations. But again, both of these are already solved for, right? B is already alone. Don't forget to check them. Now I'm going to do this mentally. All right. When I plug 5 into the original equation for B, 5 squared is 25, and then 3 times 25 is 75. You get 75 equals 75. That works. Same thing for negative 5, right? Negative 5 to the second power, negative 5 times negative 5, that's positive 25 again. And 3 times 25 is indeed 75. So both of these are good solutions. I'll circle them both. And again, you could also, if you wanted to, you'll see this in a lot of books, you could write b is equal to, because they look exactly the same, but just one's got a plus, one's got a minus, you might see it written out this way with the plus or minus 5. They mean this statement here means b equals positive 5 or b equals negative 5, right? But the same statement I have in the box above it. All right, great. Continuing on, I'm doing the same steps every time. So here's another one. So here I have, s squared, then minus 81 equals 0. Now you might also think, hey, like a while back, I put a video up on, solving quadratic equations by factoring, where you would, take everything to one side, get a quadratic polynomial on one side, 0 on the other, like this, and then factor if you could, and then use the zero product property, right? Split it up, say, hey, if this product is equal to 0, then one of the factors has to be 0, and solve that way. I could have solved the last equation, the example before this, by factoring. You could solve this one by factoring as well, right? This is actually a difference of two squares. S squared minus 9 squared is 81. And solve it the way I did way back when. But that's the thing about mathematics, though, is like, the more experience you get, very often you're going to see multiple ways of approaching the same kind of problem. So yes, I can solve this one by factoring, but I am asked to do it with that, that square root property. I'm doing these steps here, okay? So again, I notice, see how there's a variable inside a square, right? In the base of a square, s squared. And there are no variables outside that square. There's no s anywhere else in the equation. All right, so again, here's the square. All right, the only thing being raised to the second power is the s. And I would like to isolate that first, right? Get that alone on its own side. So in order to do that this time, I'll have to, add 81. All right, and if I add 81 to both sides, what do we have? We have s squared on the left equals 0 plus 81, positive 81, another positive number over here on the right. We'll get to some examples eventually where there's a negative number over there, right? So we'll end up with some imaginary solutions. But right now we're back to still having a positive. So my square is alone, and it's equal to some positive number. And now that I have it in this form, I can apply that square root property, right? SRP. I've been abbreviating it. So, for what value, when is this going to be true? What squared is equal to 81? Well, this s, this base, could be, the positive square root of 81, or s, right, the base of that power of 2, the base s could be the negative square root of 81, right? And either one of these would make that a true statement. And then, of course, I want you to simplify your radicals, right? The square root of 81 is 9. So we're getting s equals 9, positive 9, right? Or s equals the opposite of positive 9, right? Negative 9. And don't forget to check these, right? Now they work, right? Plug them in, right? 9 squared is 81. 81 minus 81 is 0. That's true. Negative 9 squared is 81. 81 minus 81 is 0. That's true. So here are my solutions. Again, you could also write this way. You could say that s could be equal to positive or negative 9. And you could write it that way as well. Right? Same thing. Means the same stuff. Great. Alright, so far in my examples, when I isolated the square, when I got it in this form, this x squared equals n, or variable squared equals n, the number on the other side has been positive so far. And you may have noticed that when that number is positive, right, my solutions end up being real numbers, right, without that imaginary unit I, right, without that square root of -1. My next example, my next couple examples actually, will change all that. So here's another one. I'm asked to solve, the variable d squared equals -72. So here it's already set up, the first step's already done, right? The square, d squared, is already alone, nothing multiplied by it, nothing divided by it, or added or subtracted from it. And then I got, just a number on the other side. And notice there's, a variable in the square, and there's no variables outside the square. There's no variable d outside that square. So I'm going to be able to use the square root property here. Alright, so the step one's done. Squares alone. Then by that square root property, right, the base on that square, the value of d could be, the principal square root of -72. Right, again, here just n is -72 now, so I'm just replacing all this with x is the d and n is -72. So d could be the principal square root of -72, the positive square root of -72, or d could be, the opposite of the square root of -72. All right. Now don't forget, I've mentioned this in previous videos, whenever you see the square root of a negative number, like I'm seeing here, rewrite it, right? It's involving that I, right? That imaginary unit I, that square root of -1. So remember, off to the side here, the square root of 72, or the square root of -72. Remember, this would be if I rewrite this as a pure imaginary, right? Remember, a pure imaginary is a real number times I. This is simply the square root of positive 72, right? A real number times I. Or sometimes it's very often where the I, the letter, the factor, is written before the radical. So you could write this as I times the square root of 72 as well. But then don't forget, right, we're also going to simplify our radicals. So this is I times, and then the square root of 72, right, I can break that up. I'm just going to skip to the end, all right? The square root of 72, 36 is a perfect square, right? That's 6 squared. 72 is 36 times 2. So I could split the square root of 72 up to the square root of 36 times the square root of 2, right? Both real numbers. And the square root of 36 is 6, right? And then you have the square root of 2 left over. And again, usually number factors that aren't in radicals are written before letter. I mean, I know that's not a variable, but it's a letter though, right? Representing a number. So usually you'll see this written as 6 times I times the square root of 2. This is the square root of -72 rewritten with that I, right? That square root of -1. This is a pure imaginary I times 6 root 2, a real number times I. All right, so going after all that, right? Going back up here, like I said, whenever you see the square root of a negative, like I'm seeing in these two, rewrite it immediately as a pure imaginary, right? A real number times I. So in the left equation here, I have d equals, the square root of -72 we saw was this, 6 times I times the square root of 2. Or, and again, because I don't have a lot of space down here, the other equation, the right equation, I'm going to write down here, d equals, the opposite of that, right? The opposite of the square root of -72, so that would be d equals, -6 times I times the square root of 2. All right, and let's check these, and I'm actually going to check these off to the side. I'll just check one of them. All right, and they both will work. but let's just check one of these, right? So don't forget to check your solutions, right? So off to the side, I'm checking, let's say, let's check the first one. All right, I'm going to plug in 6 times I times the square root of 2 for D. All right, so instead of D squared, I have in parentheses this 6 times I times the square root of 2. That's being squared. And, is this equal to negative 72? Let's see, when this is a big product, right? 6 times I times square root of 2 squared. When you have a product to a power, you can put that power on each factor. So this is 6 squared times I squared times, the square root of 2 squared. Is that equal to negative 72? And, what is 6 squared? That's 36. What is I squared? Remember, I is the principal square root of negative 1. So when you take I squared, that's negative 1 times, and then square root of 2 is a real number. So when you have the square root of 2 squared, or the square root of 2 times the square root of 2, you can put those together with the product property for radicals, right? A product of real numbers. That's the square root of 4, or just 2, right? And is this negative 72? Yes, it is, right? 36 times negative 1 would be negative 36 times 2. You have negative 72 equals negative 72. Yes, right? This is a good solution. And the same thing would go for negative, right? If you had negative 6 in there, because all that would change you'd have negative 6 to the second power, which would still be positive 36, and all the rest of it would be the same. So both of these are solutions, right? The values I can replace D with and make that a true statement. Okay. And again, you could also write this another way. You could say that the value of D could be replaced by positive or negative 6 times I times the square root of 2. This is also perfectly valid to write this box statement that way. Give me the two imaginary solutions this time. Okay. So my next example, again, same thing. I'm asked to do the same stuff, and I've only got a couple more after this. And put the steps back in there. All right, we have same thing. A quadratic equation I'm asked to solve using this square root property. So notice I will eventually be using the square root property because I do have a variable inside a square, right? This q is in the base of a square. And then outside that base with the square, there is no q. Right, so no variable outside the square. I will eventually be using the square root property. So first step, isolate the square. Again, the square here is only, the only thing being raised to the second power is the q, right? Not the 3, right? It's not in parentheses with the q underneath that exponent of 2. So just the q squared. I want to isolate that. So the first thing I do here was subtract 27 from both sides. That would leave me with 3q squared, 3 times q squared on the left equals, and then 0 minus 27, negative 27 on the right. The square is still not isolated, right? So it's being multiplied by 3, so to undo that, I would divide both sides by 3. 3's divide out here, leaving me with the q squared, right? The square is now alone on the left side. And then negative divided by positive. Negative divided by positive is negative, and 27 over 3 is 9, right? And here we go, right? Q squared equals negative 9. So now I have it in this form where, again, the x is the q, and this n is, negative 9. Now it's a negative number this time. So like the last example, we're going to see some imaginary numbers coming up here. All right, so by this square root property, right, the SRP, this q, right, the base under the square, the base is either equal to the positive square root or the principal square root of negative 9, or the base q is equal to the opposite of the square root of negative 9. And as I said in the last example, right, and in previous videos, whenever you see the square root of a negative number, like I'm seeing here, I'm seeing the square root of -9 show up in both of these results. Rewrite it as one of those pure imaginary numbers involving the imaginary unit I. So remember, the square root of -9 as a pure imaginary would simply be the square root of +9, right? That's real, times I. And again, you can throw the I in front if you want, but the square root of +9 is 3, so that's 3I. Right? So I'm going to replace immediately, right, the square root of -9 with 3I. So I'm getting Q equals 3I, or Q could be replaced by the opposite of that, -3I, and don't forget to check them. All right, now I'll just kind of say these out loud. And when if I take 3I and square it, 3I times 3I, that would be 9I squared. Now remember, whenever you hear I squared, that's -1. So when you take 3I and square it, that's -9, right? 9I squared, 9 times -1 is -9. And then -9 times 3 is -27. Then plus 27 would be 0, and so that works out, right? And the same thing would go with -3I, right? -3I squared, -3I times -3I would be +9I squared. You get 9I squared again, or -9 times 3 is -27, plus 27 is 0. Both of these work. And again, notice how when this number ends up being negative over here after you isolate the square, you have solutions that have an imaginary part to them, that have a pure imaginary showing up, 3I, -3I. And again, another way to write this would be Q equals positive or -3I. You can write it this way as well. Great. All right, my last two examples are a little different than the previous ones. You notice how in all the ones before that I've done so far, we've had our base on the power of 2, the base on the square, was just a single letter, Q squared, D squared, S squared, right? It was just a single letter. But the base under the square doesn't have to be just a single letter. It can be a whole large expression with multiple terms and a variable in it. But I still do the problems the same way. Okay, so here, the last couple of examples, I am doing that. So again, we've got the steps here. We're asked to, again, solve this equation, find, the values of y that make this true, using that square root property. Okay. So notice it is an equation where I can use the square root property. I'm going to be using the square root property. See how inside the square, right, in the base of the square, right, notice it's all in parentheses here, so this whole thing is the base, y plus 3. That whole thing's being raised to the second power. In that base, there's a variable. So there's a variable in the square, inside the base of the square, and notice there's no variable outside that square. There's no y anywhere else. So I'm going to be able to use the the square root property here. All right, so again, what is the square? All of this, right? That's the square. Right? It's y plus, that whole thing, y plus 3, that whole quantity is being raised to the second power. So it's a little different, see, than the previous examples where, the previous examples, again, you just had a single letter raised to the second. Here you have an expression with two terms, y plus 3. But it's no different. Follow the same steps. So I isolate the square. Well, the square is already on its own side. There's nothing multiplied by it. There's nothing it's divided by. There's nothing it's added to or subtracted from. And then on the other side, you have the number. So here, the x in my little form here, the x is this y plus 3. And the n is the 100. So now that I've isolated the square, we can use our square root property. And by the square root property, this will be a true statement when the base, now again, not just the one letter, but when this base, when this y plus 3 is equal to the positive square root of 100, right? Or, and when the base on the square, the y plus 3, when that's equal to negative square root of 100. Right? In either one of those cases, this will be a true statement that I started with. And of course, again, we simplify our radicals. Right? So this first equation is y plus 3 equals positive 10. And then this second equation is y plus 3 equals, the opposite of that, negative 10. Now comes, step 3. We really haven't done step 3 for anything because, when I use the square root property in my previous examples, the two equations were already solved for, right? The variable was already alone, but not this time, right? Now step 3, solve these resulting equations. And in both of them, I would just simply have to, to get y alone, I would simply subtract 3 from both sides. So I'm going to do both of them at the same time here. And this left equation, we get a value of y equals, 10 minus 3 is 7. Or, then this right equation, y on the left now equals, and then negative 10 minus 3, negative 13. And don't forget to check them. All right, now that we've solved, let's check back on the original equation. And this is a pretty nice one to just say out loud. We can check them out loud. When y is 7, 7 plus 3 is 10. 10 to the second power, 10 times 10 is indeed positive 100. So 7 works. Y equals negative 13. Negative 13 plus 3 is negative 10. And, negative 10 to the second power, negative 10 times negative 10 would be indeed positive 100. So both of them work. All right, now here's one where I can't write it another way. I can't write y equals plus or minus something because they're not the same, a number and its opposite. It's not like 5 and negative 5. I can't write plus or minus 5. This is 7. This is negative 13. They're not opposites. So I'm not going to write it some other way with y equals, plus or minus something. Right? This is it. My solutions are 7 and negative 13. Great. All right, and my one final example, where I'm doing, again, exactly the same steps and leaving them up. I'm asked to solve this quadratic, using the square root property. And you can tell right away that you can use the square root property in this because inside the square there's a variable, right? This has this square, this power of 2 has a base of, this q minus 5, this whole thing, right? It's in parentheses under the 2. So there's a variable inside the square, and then look outside the square. There is no q, there is no variable. So this tells me I can, solve this through use of the square root property. But first things first, I have to isolate the square. All right, so the square this time, I'll just underline it instead of put it in a whole box. That's the square right there. This quantity q minus 5 squared. Notice there is something else with it over here. It's not alone. It's got the plus 20. So in order to get rid of that, I would subtract 20 from both sides, leaving me with, the quantity q minus 5 squared on the left equals, and then 4 minus 20 is, negative 16 on the right. So it's just like the form here, right? The square is alone. But instead of x squared, I have, x is the q minus 5, and the n is the negative 16. And notice that is a negative number. And you've seen in previous examples, when that's a negative number after isolating the square, you'll have solutions that have the imaginary unit I in it. You'll have imaginary parts to your solutions. All right, so now that I have the square isolated, by that square root property, right, SRP again. This base, right, this q minus 5 could be equal to the principal square root, the positive square root of negative 16, or again, this base, this q minus 5, the base of the square, could be equal to the negative, or the opposite of, the square root of negative 16. All right. And then, as I've mentioned several times now, whenever you see the square root of a negative number, which I am seeing here, you should automatically, instantly rewrite that as a pure imaginary number, right? A number with I attached to it. So the square root of negative 16, as a pure imaginary, as a real number times I could rewrite that as the square root of positive 16 times I, right? Again, I is not in the square root, right? Don't make that too long. And what is the square root of positive 16? The principal square root, that's 4. So this is 4i, right? The square root of negative 16 is, as a pure imaginary, is 4 times I. All right, so rewriting that in my equations, this first equation on the left here, I have q minus 5 equals, the square root of negative 16, as I said, is 4 times I, or 4i. Or this other equation, q minus 5, is the opposite of that, right? The opposite of the square root of negative 16, or negative 4i. And then comes step 3, right? Solve the resulting equations, right? Which I have to do here because notice the variable q is not alone. So that's very easily done in both of these, right? In both of these, I would simply, to get q alone, just be adding 5 to both sides. All right, so on the left equation, I have q on the left equals, now you can put 4i plus 5, but very often you'll see that, when you're writing out solutions that have an imaginary part, if you recall a video earlier on complex numbers that I put up, remember that a plus bi, this was, where a and b are real. You have a real number plus a pure imaginary. This was called that standard form for a complex number. Remember, every number is a complex number. Every number we've seen so far can be written like this, but typically in most texts you're going to see numbers written in this form, where your real number is first and then your imaginary number, that term, is second. So yes, you could write 4i plus 5 equals q, fine. But what's the real number? That's positive 5, and then the imaginary part, the imaginary number, positive 4i. So I'm going to write that, q equals 5 plus 4i. Or, then doing the same thing here, adding 5 to both sides, we get q equals, and then the same thing. You could write negative 4i plus 5, right? That's not wrong. It's just very often you're going to see solutions in texts, or you're going to be asked to write solutions in this standard form for a complex number. All right, so I'll put the real number first, the positive 5, then the imaginary term, the imaginary number second, the negative 4i. All right, and these don't go together, right? One has an I attached, the other does not. So don't make this 9 times I or something, and don't make this 1 times I. That's real, that's imaginary, they do not go together. And then, of course, check them. All right, now let's see what happens when you check them. When q is 5 plus 4i, put it up here. You'd have 5 plus 4i, but then minus 5 in the parentheses here. Well, 5 plus 4i minus 5 would get rid of the 5, leaving you with 4i. So this, in parentheses, becomes 4i squared. And what's 4i times 4i? That'd be 16i squared, or 16 times negative 1, which is negative 16. So we did negative 16 here, plus 20 is 4, and that is correct. And the same thing would happen with 5 minus 4i. The 5 would get subtracted, and then negative 4i, when squared, would be, again, 16i squared, or negative 16, and then plus 20 is 4. So both of these work back in my original equation, q equals 5 plus 4i, or q is replaced by 5 minus 4i. Both are good solutions. And look, now these I can do the plus or minus thing with. They look exactly the same, except there's a plus here, minus there. Right, and in fact, these are called, complex conjugates. I did a video on those in the past. You can look that up, complex conjugates. But I could also write this, that Q equals, they both have the same 5, and then, one has the plus, one has the minus for I in the second term. I could write this as well if I wanted to for the solutions. Great. All right. But I think the main thing to take away from this video are these steps here. All right. And also when to, what to look out for to see if you can actually, solve an equation using the square root property. Is there a variable in a square? First off, is the square the highest power, right? Because if there's a third power or a fourth power, then it's not a quadratic equation anymore, right? So first off, is it a quadratic? Is there a variable to the square the highest power? Then, is there a variable inside the square? Check. And then is there a variable outside the square? If there's no variable outside the square, then you will be able to use this square root property. You might follow these steps, and of course check your solutions when you're done. All right, great. All right, and as I like to say at the end of these videos, do the best you can to learn the material on your own before you go looking for help. I have found over the years that when people take the time and the effort to learn something on their own, they tend to remember it better and also remember it for longer. And they're more proud of themselves, right? Have more confidence in their own abilities. So of course, read the material, right? Read through the author's examples. Perhaps even try to work out the solutions to an author's examples before you see how the author did it. And then compare your work with the author's and see if you can learn from some mistakes there. Obviously work on tons of exercises, practice problems, look up solutions to those if they're made available, just so you can check yourself and keep track of your progress, see how you're doing. And don't give up on a problem or an exercise after 1 or 2 attempts. Don't give up so easily. Very often in mathematics, there are several approaches that'll work for any particular problem. Right? You even saw in this video. I said it, I didn't do it, but there were some of these equations here that I could have solved with the square root property, or I could have solved them by factoring. Right? So yeah, like I said, very often there are several approaches that'll work for a particular problem. But if after several attempts at a problem, several different approaches, and you're still not getting it, maybe you should go back and read the material again, maybe even a third time, more slowly, more deliberately. Take good notes, because if you've been working on some problems, there's a good chance you have a better idea as to what the author wants from you, what the author's expecting of you. So then when you go back and read again, or that third time, you'll know better what to look out for in the reading. And hopefully some things will pop out at you that didn't pop at you the first time that you read through, and it'll make working on the problems that much easier. But if after that, if after several read-throughs of the material and several attempts at problems, you're still not understanding, still not getting it, it's not a sign of weakness whatsoever to go out looking for help. That is what other people are there for, to help you. So ask a teacher, a tutor, a friend, someone in your class who knows the material well and is willing to help. Look for supplemental materials online. There's tons of it out there. Look for videos on the subject. There's loads of those too. Videos like this one, or plenty of other ones out there that are better than this one. I assure you they're out there and they're easy to find. But just keep at it. Stay persistent, keep practicing, don't give up. And above all, and I think the hardest thing for people to do, is to stay positive about the subject. Try to have fun with it, and believe in your abilities even when you're frustrated, even when you're struggling and failing and making mistakes. Because if you can push through and figure out how to fix your mistakes, you can push through your frustrations. If you can do that, those times when you're struggling and you're frustrated and you're failing and you're making mistakes, those are the times when you can learn the most, and also learn the most deeply. because if you push through and are able to fix your mistakes, you're going to remember that material far longer and far better than someone who got it right the first time and just breezed through and then they never think of it again. All right. So please stay persistent, keep practicing, stay positive, and don't give up. And I just know you'll get it. All right, and thank you very much for watching.